Hey there everybody, Mr. D here, and in this video we are going to recap graphing rational functions. Rational functions, again, are anything in which you have an x in the denominator, or a variable in the denominator of your function. Alright, so we'll glaze past the warm-up here. Let's go ahead and take a look at some example graphs of rational functions. So these three graphs here, these are all rationals. You'll notice within each we have vertical asymptotes and horizontal asymptotes, and our graph itself is disjointed. Sometimes our vertical asymptote will actually be a slanted asymptote, but we'll see that down the road. But just notice the different features here. As we go left to right, our function is always defined except for asymptote values. Now, if we were to pick apart some of these key components here, we could look at a graph and just get domain, right? I've got the domain. It looks like everything except for -1 is fair game. So negative infinity, that's a terrible infinity, to -1, and then -1 to positive infinity would be my domain. I've got a vertical asymptote at x equals -1, and notice the asymptote values also tie into the domain. Curious, interesting. X-intercepts are any time we have a graph crossing the x-axis. Well, it looks like it crosses right here at the origin, so we have an x-intercept at 0, 0. Y-intercepts. Y-intercepts are any time it crosses the y-axis. Well, the origin is both x and y-axis, so we've got kind of a 2-for-1 deal. That's also going to be 0, 0. Let's go ahead and tackle this next one. Here I've got the function. Let's take a look at the graph. The domain, it appears to be everything except for my vertical asymptote value, which is 3. So we're going to have negative infinity all the way up to 3, and then 3 to positive infinity, because there's a vertical asymptote at x equals 3. These values match, just like these did. Coincidence, crazy. Then we have our x-intercept. Well, our x-intercept is right here at 1. So we'd write that as 1, 0. Y-intercepts, where does it hit the y-axis? I don't even know what that value is. We're going to guess. I'll say 1/4. So we have a y-intercept of 0, -1/4. All right, let's take one more look at a graph, and then we'll start picking apart patterns. All right, domain. Well, it looks like I've got 2 vertical asymptotes, so that's 2 breaks in my function. 2 breaks in the domain. Those happen at -2 and at +2. So my function is defined everywhere except for the specific values negative and +2. That's because there are vertical asymptotes at negative and +2. Coincidence, crazy. X-intercepts. Where does this thing hit the x-axis? Some of you might be tempted to say here at 4, -4. It doesn't actually hit. It gets infinitely close. This is an asymptote, so our graph is infinitely getting closer to it. It never actually hits it. Imagine kind of like a freeway entrance ramp that just merges forever. You never actually get into the lane, you just get infinitely close. So this thing has no x-intercepts. None. Does not exist. And then our y-intercept, right about there. So again, I don't know what that is. My graph isn't detailed enough. I'm going to guess, same as before. We'll call it -1/4 or 0.25, whatever you want to do. All right, so now let's take a look at the functions themselves and see if we can draw any conclusions. Now, some of you guys might remember this from pre-calc, and if that's the case, good on you. We already kind of discovered or mentioned that the asymptote value is always reflected within the domain. So we already mentioned that. But let's look at the original function as well. Something weird happens at -1. Well, if I look at the original function, -1 is where I'd get a 0 in the denominator. So that might have something to do with it. That denominator is going to result in vertical asymptotes. And vertical asymptotes will result in domain restrictions. Well, if the denominator results in something, then surely the numerator probably does as well. So if I look at the numerator here, 2x, negative x plus 1, no x at all, just a 1. Well, now I'm starting to notice that might have something to do with my x-intercepts. Because I had an x-intercept here at 0. 2 times 0 gives me 0. Over here, negative x plus 1. Well, if I plugged in 1 for x, negative 1 plus 1 is a 0. So anytime I get a 0 in the top, that corresponds with an x-intercept. Last one, there was no x at all. There was no variable. The previous ones had variables. This guy doesn't. Well, that kind of explains why there was no x-intercept. So in general, to get a vertical asymptote, you are going to look in the denominator. Set that denominator equal to 0. Find those domain restrictions. To find an x-intercept, you are going to look in the numerator. What values for x would make that thing equal to 0? And then there's the y-intercept. The y-intercept we don't place as much attention on simply because sometimes it's helpful, sometimes it's not. All you have to do is just plug in x equals 0 and figure out what the y value is from there. All right, so now we have all the components to figure out some of these features of our graph. Now let's get into end behavior. End behavior means as my graph goes really far to the left or really far to the right, what's it doing? The way we express really far to the left, really far to the right, is with this notation here, as x approaches infinity. So as x approaches infinity, if you were to visualize a coordinate system, a graph, if x approaches infinity, it's going to the right. Negative infinity means it's going to the left. So I want to know what's going on the right side, what's going on the left side. This f of x, that's just a fancy way of saying what's the y value doing. So let's look at our graph here. All right. As we go forever to the right, this graph is getting infinitely closer to this horizontal asymptote, which has a value of 2. If I go forever to the left, same thing. It's getting infinitely closer to a value of 2. So as we approach negative or positive infinity, our graph is approaching a y value of 2. That's because we have a horizontal asymptote at 2. The range for this function, if I were to look at this thing going from bottom to top, low to high, every y value is included except for, in this case, 2. So we're going to have negative infinity all the way up to 2, and then 2 to infinity. Let's do the next one here. End behavior, if I go forever to the right, it's approaching negative 1. Forever to the left, it's approaching negative 1. Well, that leads me to believe that there's a horizontal asymptote at, you guessed it, negative 1. So the range for this thing would be negative infinity to negative 1, and then negative 1 to infinity. Let's take a look at that third graph that we saw before. As we go forever out to the right, it's getting closer and closer to the x-axis. Same thing forever to the left. So we are approaching a y value of 0 because there's an asymptote at y equals 0. The range for this would be negative infinity to 0 and then 0 to infinity, if we were to read that bottom to top. So now let's look for patterns here. Well, I'm seeing this one has 2, and I see a 2 up there. I don't know if that does anything. This was a negative 1. Not really seeing a negative 1 up here. I guess there's a negative attached to that x value. So there's that. This one was approaching 0. I'm not really seeing 0 anywhere here, but that could also just be the fact that there was no x. I don't know. Let's see. For a horizontal asymptote, there are 3 different scenarios. The way you figure out the horizontal asymptote is you look at the degree of your numerator and the degree of the denominator. And when I say degree, what I mean is the exponents attached. So in this case, we have a degree of 3 over degree of 4. And we want to figure out, is the top bigger, smaller, or tied with the denominator? Or some people say, is this function top heavy or bottom heavy, or neither? Is it a tie? So when you do this, you're going to look at the highest exponent from the numerator and highest exponent from the denominator. Those are the only things you care about. And then you're going to ask yourself, which of these scenarios describes it? Is the numerator smaller? The degree of the numerator, if that's smaller, then it's just automatically going to be 0, defaults to 0. If it's a tie, they have the same degree, then it's going to be the coefficients ratio, so you're going to divide top divided by bottom. And if the numerator is bigger, if it's top heavy, you have what's called a slanted asymptote. All right, so let's take a look. Here I've got 3x squared over x. Well, x squared is clearly more x power, higher degree. So we'd have a horizontal asymptote at 3 over 1 times x. So that is a slanted asymptote, not a horizontal asymptote. We'll call that a sassy. Next one, I've got a 5x over 3x squared. Well, this one's clearly bottom heavy, so it falls into this category. It's bottom heavy, which means it defaults to 0. Last one here, I've got a negative 3x cubed and a negative 4x cubed. Well, that's a tie. So I'm going to take the ratio of coefficients there, negative 3 divided by negative 4. Well, that simplifies to just 3/4. So we'll have 3 possible scenarios anytime we're trying to get our asymptote values. Okay, let's take a look. We'll probably do, we'll see how time goes. We'll do 2, maybe 3 of these. All right, we are going to find all of this key information here without graphing. First thing, I'm noticing in the numerator, there is no x, which means there are no x-intercepts. Next, I'm looking in the denominator. I see x plus 3. Well, I know that that is not allowed to equal 0. So x cannot equal negative 3, because negative 3 plus 3 would be 0, which means I have a vertical asymptote at negative 3. Now that helps me find the domain as well. Negative 3 is off limits. So negative infinity all the way up to negative 3, and negative 3 to positive infinity is my domain. Horizontal asymptote. Well, there's no x's up top. There's a single x down below. This is bottom heavy. So if this is a bottom heavy function, our horizontal asymptote defaults to y equals 0, which then tells me my end behaviors are going to approach 0 as we go really far to the left, really far to the right. Now the only thing that's left to do is find our y-intercept. Now the y-intercept has an x value of 0. The way we plug this in is just throw in 0 for x and see what you get. So if I plugged in 0 for x here, that's 3 over 0 plus 3. That'd be 3 over 3. That's just 1. There we go. All right, let's do one more. Then we'll call it a day here. We will do this third one here. X minus 1 over x squared minus 9. Oh, look in the top. X minus 1. Hey, I've got an x up there. That means I'm going to have an x-intercept. 1, 0. It's going to be my x-intercept. Then I'll look in the denominator. X squared minus 9. That is not allowed to equal 0, which means x squared can't be 9, so x cannot equal plus or minus 3. So I'm going to have 2 vertical asymptotes at negative 3 and at positive 3. That also tells me some information on the domain, because my domain could be everything except positive and negative 3. So my domain is going to be negative infinity to negative 3, negative 3 to positive 3, and then positive 3 to infinity. My horizontal asymptote, I'm going to look at the degree of the numerator, so that's 1. Degree of the denominator, that's 2. This thing is bottom heavy, so we're going to default to y equals 0. which means my end behaviors, if they were down here, would also be zeros. And then lastly, let's get the y-intercept. To find the y-intercept, we're just plugging in 0 for x and see what we get. So that'd be 0 minus 1 over 0 squared minus 9. That's negative 1 over negative 9. Well, that's just 1/9. Cool. All right, that is it. That is all, folks. You know the drill. If you have any questions, please let me know. And as always, good luck, have fun, be safe, roll tide.